Hi and welcome to video 9 of this Unit 4 Topic 2 Differential Equations Specialist Mathematics curriculum video. So we're going to be talking today about the logistics curve, which is a very specific case of differential equation applications, and in particular it's little bit like our Newton's law of cooling work, but this is probably even more specific. It's a modelling application for population growth, which makes a lot more sense than the one that we currently use. So let's have a look. The logistics curve. The standard population model looks like this purple one, and you can see that it's just growing and growing. But we know that at some point there's going to be some moment where there's just too large a population. And a really common example of this is you're looking at a population of animals on an island. And it gets to a point where the island just can't sustain that population, so the population starts to stagnate and hit a natural limit or a natural maximum. And so instead, really, that green curve, the kind of S-shaped curve there, that is a much better model for population growth, because we know that when the population is low down here, the growth of the population will also be low because there's not as many animals within the species to breed. As the population grows, so does the rate of change of the population, because it's growing as the number grows, therefore the rate can grow. But at some point it starts to peter out. This growth can't happen anymore. So you see there's this relationship between the rate of change and how far from zero you are, but also between the rate of change and how far from that natural limit you are. And that's a much better model for population growth. It looks like this. And population growth varies as well. There's obviously other things at play, such as predators, food supplies, natural weather events, etc. But this is a really nice way to do that standard model population growth that fits a context a little bit better. So here is some stuff from a textbook. This is one way of looking at it, and I just wanted to introduce that to you so you see it. It's the textbook that my students will use. But we are going to develop this model, and I'm going to show you how it develops. So in logistics models, we say that the rate of growth is both related to, so both proportional to the population, but also proportional to the upper bound minus the population. So let me go back up to the model here and just show you what I mean by this. This point here, that represents some population P. So P is this gap. We're saying as P increases, the rate of change increases. But also, this is M, which is the maximum, or the limit, the natural limit. So M minus P is this gap. So what happens is we're saying that the rate of change is proportional to both the size of this gap and the size of this gap. If this gap is really small, like it is up here, then the rate of change is quite low. If this gap is really small, like it is down here, then the rate of change is quite low. Now, I've managed to ruin that diagram. Let's go back down to our working. So with that in mind, we say that dP to T is proportional to P times M minus P. And I just want to make a note, we use the Cambridge textbook, and in the Cambridge textbook it says dP to T is equal to, we're going to, in fact, I'll write this down now. For me, this means that dP to T is equal to Kp M minus P. In the textbook it says dP to T equals Rp, 1 minus P over K. Now, if we expand this out, we get R over K, and then we get K equals RK. And they call K the carrying capacity, and K is my M, maximum population. And R is called the growth parameter. Well, R is kind of related to the K value I've got in my model, the lowercase k constant. So I'm saying it's the same model, different package. But I do think my model links better with the differential equations we've done previously. So I'm going to run through with my model, and you can build this model. Actually, the most robust and capable students within this topic will really have a good understanding of the link between both and how to use both, which is really something to aspire to. So let's work through developing the logistics model from the rate of change model that we're given here. So I wanted to solve this differential equation. What this means is that I'm going to take, I'm going to leave the P here, but I'm going to have P M minus P there, and that's going to be equal to KT, sorry, not KT, K dt, and I'm going to integrate both sides. Now, in the past, I've integrated to P over P pretty easily, but in this case, I've actually got partial fractions, so I have to be a little bit careful. So let's do a little bit of work on our partial fractions here. 1 over p m minus p, I'm going to say that's equal to a over p plus b over m minus p. I'm going to multiply by p times m minus p, and that gives me 1 on this side, and this is actually an equivalent statement, so a and b make it work for all cases. A m minus p plus b p, and when I rearrange that, I get b minus a p and then plus am or ma. I'll do it alphabetically, am. So that's my expansion and rearrangement. So this is the constant value here, and this is my coefficient of p. So that means that this must be equal to 0 because there's 0p over here, and this must be equal to 1 because there's 1 there. So what I'm going to get is b minus a equals 0, but am equals 1, and so therefore a equals 1 over m, and that means that b also equals 1 over m because b equals a. And so we get this. It's going to get a little trickier now. The integral, I don't need an equal sign there, of a over p, which is 1 over m over p, plus b over m minus p, which is 1 over m over m minus p, dp is equal to kt plus some constant c. And I'm going to leave it like this because I can take 1 over m out as a common factor, 1 over m, and I've left with the natural log of p, population is always going to be positive by the way, plus the natural log of m minus p, also always positive, and that equals kt plus c. So that's where we're at so far. Now I'm going to take this m factor at the front here and take it across the other side, and I get log p, well actually I'm going to combine these logs. I get log of p m minus p sorry, I have missed something here, which makes this work a bit better. When I integrate m minus p, I'm integrating with respect to p, which means I have to divide by -1, because I've got that, the derivative of the inside is -1, and so I get -1 there. So this means I get log of p minus log of m minus p, and over here I get mkt plus some constant, and the constant is it just remains, it's still a constant irrespective, so it doesn't matter about the m incorporation in there. And now I'm going to bring these together, so I get log of p over m minus p, and that works more as I expected, mkt plus c. I'm going to rearrange, I get p over m minus p equals e to the mkt plus c. So keep in mind of course that c, m, k, they're all unknown constants, and they're constants specific to the situation. P is a function of t, so I want to get p by itself, and it should be some function of t. So I'm going to write this down as p equals m minus p times by a e to the mkt. I've just taken that plus c and made it a. Now, it looks pretty good. I've got p by itself, but I've also got another p here, so I have to do a little bit more work. So that will be to write p equals ma e to the mkt, and if k wasn't important and m wasn't important, I could combine these two, but I'm not going to combine them yet because k is related to the growth rate and m is the maximum capacity, so it might be important. Minus pa e to the mkt. I take that over, so I get p plus pa e to the mkt, because ma e to the mkt. I factorise the p out, p1 plus a e to the mkt equals ma e to the mkt, and then I divide through, which gives me p is equal to ma e to the mkt over 1 plus a e to the mkt, and that's my model. Now, there's a couple of things I can do with this. The The first is that we often incorporate the m and the k together. So we say something like let mk equal just k or k1 or something like that. And so I get mae to the k1t, but I'll just call it k. It's just incorporated into the k. 1 plus ae to the kt. That's the first thing. The other thing we can do is you'll see here that we've got e to the kt twice. We can make it so we've only got e to the kt once, which sounds weird, but it's going to help us a little bit in terms of interpretation. If I multiply by e to the negative kt and e to the negative kt on top and bottom, I actually get this. That cancels and that cancels, and I'm left with ma over e to the negative kt plus a, which is a bit simpler. A is a constant, and m is a constant, and k is a constant, and so it's just in terms of t. Either of these really, though, either of these work, so they're the model that I will typically use. If you go back up to this work earlier, this will give us a slightly different model where k is equal to r over some constant and m is equal to k. You can do that as well if you want to, and have a look at the textbook if you want to see different variation in this model. But this is nice, it works, and we can solve problems using it. So that's the end of this video though, and tune into the next video and I'll be talking about a different example and showing you how this works. All the best.